Today, we're diving deep into the secret language of all the gadgets that you use every single day. We're going to pull back the curtain and see how they really work.
So think about it for a second. Have you ever pressed a button on, say, your microwave and just wondered, how does that simple little push translate into action? How does it actually know what you want it to do? Well, I can tell you it's not magic. It's actually a perfectly coordinated team of tiny electronic components all working together in perfect harmony. And over the next few minutes, we're going to build our own gadget, conceptually at least, and meet that entire team piece by piece. All right, first things first. Every team needs a leader, right? A central command. And in the world of gadgets, this is the brain of the whole operation. So say hello to the microcontroller. The best way to think about this is as a complete miniature computer that's been squeezed onto one single tiny chip. Its entire job is to run one specific program over and over, controlling everything else. It really is the boss. Okay, so we've got our brain. But, a brain that can't communicate with the outside world is, well, it's pretty useless. It needs ways to show us what it's doing, to tell us what's happening. It needs outputs.
And one of the most classic, instantly recognizable ways for a gadget to talk to us is with this guy, the 7-segment display. You've seen these literally everywhere, from alarm clocks to ovens to scoreboards.
And the idea behind it is just beautifully simple. It's really just 7 individual LEDs arranged in that classic figure-8 pattern. The microcontroller, our brain, sends a little pulse of electricity to just the right combination of those segments to light up any number from 0 to 9. It's just a fantastic example of a simple design doing a really important job. Now, there are a couple of different ways to wire them, but the core idea is exactly the same. The microcontroller is like a tiny, lightning-fast light switch operator, just flipping the right segments on to show you what you need to see. Okay, our gadget can show us numbers. Now let's give it an actual voice, using a buzzer. You've got 2 main kinds. The active buzzer is super simple. Give it power and it makes one single sound. Beep. But the passive buzzer, that's the musical one. The microcontroller has to send it a specific frequency, which means it can play different notes and even little melodies. All right, our device can show us things and it can make sounds. That's great, but for it to be truly useful, it needs to be able to listen to us. It's time to give it some inputs. And you really can't get any more fundamental than this, the humble push button. It's the most direct, simple way for us to give our gadget a command. But here's a little secret, a gremlin hiding inside almost every button. When you press it, the tiny metal bits inside don't just connect cleanly once. For a few thousandths of a second, they actually bounce. To a super fast microcontroller, this messy bouncing looks like you're frantically smashing that button dozens of times. So engineers have to debounce that signal. You can do it with hardware by adding a little circuit to physically smooth out those electrical bumps, or, and this is way more common, you do it with software. The code basically sees the first press, that intentionally waits a tiny moment for the bouncing to stop before it checks again. It's a really clever way to solve a physical problem with pure logic. So, one button is simple enough, but what about something like this? A keypad with 16 different keys. Now you might think that means you need 16 separate wires going to the brain, right? That would use up a ton of its connection points. But amazingly, you only need 8. So how on earth does that work? Well, the secret is a really clever trick. The keys are wired into a grid, a matrix of 4 rows and 4 columns. So instead of watching every key all at once, the microcontroller sends a quick electrical pulse down one row at a time, while it listens on all 4 of the columns. When it hears that pulse, it knows the exact intersection, which row it just activated, and which column it heard the signal on, pinpointing the exact key you pressed. It's a brilliant way to do more with less. So, our gadget has a brain. It can talk, it can listen. Now it's finally time to do something, to actually make things happen in the real world. See, a microcontroller signal is tiny. We're talking just a few volts. That is nowhere near enough power to turn on a lamp or spin a big motor. And that's where the relay comes in. It's basically an electrical lever. The microcontroller sends its tiny signal to a little electromagnet, which creates a magnetic field that pulls a physical switch closed on a completely separate, high-power circuit. It's the perfect, safe way for the tiny brain to control the big muscles. And for any job that requires incredible precision, you'll find a stepper motor. Unlike a normal motor that just spins and spins,
A stepper moves in exact, tiny, perfectly repeatable steps. This is why they are the absolute heart of things like 3D printers and CNC machines. The microcontroller can just tell it, move forward to 115 steps, and it does, perfectly. It doesn't even need sensors to check its work. And when it stops, it locks into place with some serious holding strength.
Okay, so we've met the whole team of components, but putting them all together to create a real product, well, that involves making some really tough choices. This is what we call the designer's dilemma.
For anything that runs on a battery, power is everything. And managing it really comes down to 3 key things. First, you have to monitor it. You need to know exactly where every little bit of energy is going. Second, you control it. If a part of the system isn't being used, you put it to sleep to save power. And third, you optimize, constantly choosing the most efficient parts and writing the leanest code possible to squeeze every last drop of juice out of that battery.
And maybe the biggest trade-off of all is the brain itself. Do you use a flexible general-purpose processor that can do a lot of things pretty well, kind of like a Swiss Army knife? Or, if you're making millions of these things, do you design a custom chip, an ASIC? It's built from the ground up to do one single thing absolutely perfectly. It costs a fortune to design, but in mass production, you get unbeatable performance and efficiency.
So this team, the brain, its senses, its voice, and its muscles, it's the foundation of every single smart device we rely on. And that leaves us with a really fascinating question to think about. As our devices get even smarter, what new senses will they need to better understand our world, and what new muscles will they need to change it?